use Galerkin method to find the displacement of the system shown. So this is the problem given: a bar which is having area A, Young's modulus E, subjected to a axial load P, which is having length L. Now, so solution for this problem. Now first we have to define the boundary condition. So boundary condition at x is equal to 0, at x is equal to 0, u is equal to 0, right? Now at x is equal to L, dou u by dou x, that is equal to P by AE. So these are the boundary conditions. Okay, this is nothing but stress is directly proportional to strain. Now, so first step, that is formulate differential equation of equilibrium So for a bar problem, differential equation of equilibrium is AE into dou square u by dou x square plus u naught is equal to 0. Since there is no traction, therefore this is not there, right? So AE, therefore this equation will be AE into dou square u by dou x square, that is equal to 0. So this is the differential equation of equilibrium. Next, second step, that is assume a polynomial displacement function. So next step is assume a displacement function it may be any polynomial or trigonometric. So here let's assume it's a polynomial. So u is equal to a naught plus a1x plus a2x square. Right. Next, a0, a1, a2 are generalized coordinates. Now at x is equal to 0, we have, if we substitute x is equal to 0, we have u is equal to 0. That is the first boundary condition. Now second boundary condition, this is first boundary condition. Second boundary condition is at x is equal to L, dou u by dou x is equal to P by A. Now if we apply these boundary conditions, apply the above boundary conditions, we get, if you substitute at x is equal to 0, u is equal to 0 here, you get from boundary condition A, okay, from right, that is at x is equal to 0, u is equal to 0. If you substitute here, you will get a naught is equal to 0. So therefore we can write u is equal to a1x plus a2x square, right? Now if you differentiate dou u by dou x, above expression, you can write it as a1 plus 2 into a2 into x. So we know that dou u by dou x is nothing but p by ae, that is at x is equal to L. So if we apply, so from that is boundary condition B, that is at x is equal to L, we can write dou u by dou x is equal to p by ae. So therefore now if you substitute in this here, you can write it as p by ae, that is equal to a1 plus 2a2, in place of x we substitute L. Now that is nothing but we can write a1 is equal to p by ae minus 2 L into a2. Now if we got a naught and a1, substitute in displacement function, we can write substituting the value of a naught and a1 here, we get u is equal to p by ae, that is a1, so a naught is 0, into x, in place of a1 substitute this, so plus, sorry, minus 2l a2 x plus a2 x square. Now that is u is equal to p by ae into x plus, if you take a2 common, you can write x square minus 2lx into a2. So third step is substitute the displacement function into differential equation. Okay, so now we have already applied the boundary condition. So next we will substitute, so this that is into differential equation or governing differential equation that we have just now obtained for a bar problem. So now as the polynomial function, so this function is a approximate function, So if we substitute the value of u, that is this here, the resulting answer will be is not 0, you will get some error or some value, some positive value you will get. So that is nothing but residue. So we can write here AE dou square u, that is u is this, we are substituting, divided by dou x square, that is equal to r, some residue. Okay. Now I'll substitute in place of u this value, we'll get now, so this is u, so we need a dou square u, right? So now we can, if you differentiate dou once, we get p by AE plus x is 2x minus 2l into A2. So once again, if we differentiate, then write it is 2 into A2. Okay, now if I substitute this here, we can write R is equal to 2 into E into A into A2. So this is the residue. Next, fourth one steps, that is use the Galerkin's formula. That is from weighted residual definition. We have 0 to L Wi of x r of x into dx is equal to 0. Now here the value of I depends upon the number of unknowns. So if I substitute I is equal to 2, I can write 0 to L W2 of x into r into dx is equal to 0. So now substituting for W2 of x into r, now that is nothing but integration of 0 to L. So W2 of x, that is, so as we have only one unknown, that is A2, so W2 of x is x square minus 2lx. So substitute x square minus 2lx into r is nothing but 2ea A2, so that is 2 into E A2 into dx is equal to 0. Now if you integrate this, you'll get 2ea A2 into x cube by 3 minus 2l into x cube by x square by 2 that is equal to 0. So if we substitute limits, we can write 2e e a2 into minus 2l square divided by 2l cube divided by 3, that is equal to 0. So from this we can write a2 is equal to 0. So the next, so we got now a1 is 0, a2 is also 0. Sorry, a1 is this p by ae into 2l a2. a0 is 0 and a2 is 0. So therefore we can now find fifth step, that is find the unknown displacement. So substituting the value of a2 is equal to 0 in, so this expression, that is the expression we got after applying the boundary conditions. So we get, so let's say I denote it as star. In star we get u is equal to, so this will become 0, okay, because a2 is 0. So can write u is equal to p by ae into x. Right, now at x is equal to L, you can write displacement u is equal to PL by AE.